Welcome back, everyone. We have 7.2 transforming logarithmic functions. And we have two learning goals: to evaluate logarithmic functions and to transform logarithmic functions. Okay. Now let's break down what is a log, what is a logarithmic function. Okay. Now a logarithmic function is it looks super complex, it sounds complex, but it is just the inverse of the exponential function. Okay. And that's crucial there. We are just asking the reverse question. How do we get back to where we were? Or in this case, what was the power that it was raised to? Okay, so this top one we have here, this b to the power of x is equal to a, this is our exponential form. Okay, this bottom one here is our logarithmic form. Okay, now notice that we're using the same variables here. So this base is the base number, but it's also the base number for the log. Okay, now the a is in a different place. This a is for our answer. The a is here now. Okay, and the x is our answer. Okay, so it's asking a very similar question, and you can think of it this way. We take the base to the power of x to get the answer. But when we write the log, you're only going to have this. You're going to say something like this. We're going to go, that's LG. Okay, we're going to go log, let's say, of 3, or log 3 of 10, all right? And that's all you get. And so we're asking, hey, we took 3 to the power of something to get 10. What was that number, okay? And there's lots of different ways to try and figure out what that number is. We're going to kind of focus on some of the simple ones because we're not doing logarithmic properties today. We're just going to be kind of doing, the easier ones that we can think about what the answer is. Okay? So, all right. We have evaluating logarithms. We're going to do an I do. This problem was actually supposed to be log 5 of 0.2. And I'll show you how to do that when we get there. Okay? Now, little disclaimer before we actually do these. All right? There are a lot of ways to solve logarithms. We are focusing on some very simple evaluating, okay? The next lesson will be the properties of logarithms, and we will go really in depth with better ways of solving it. But I want you to today to be able to evaluate simple logarithms by thinking about it more as an exponential function and approaching it that way so that we get comfortable with logs, all right? And you're going to see with logs, we generally just think of these in terms of their exponential function and their exponential form because it's much easier to think about, okay? Now, in the previous one, right, you saw that we can set things equal to x, and that's really kind of the first approach that I would take here is set this equal to x so that we can use our circle method. We can think of this first one, log 4 of 64 is equal to x, as really an exponential form of 4 to the power of x is equal to 64. Okay, and this is sometimes again called the circle method. So I'm going to think of it this way. 4 to the power of x is equal to 64. Okay, now if you think of it this way, you can kind of just really think about what x equals, right? And I can write it out. I know I'm going to have to take 4 and multiply it a bunch of times. Well, 4 times 4 is 16, right? And or multiply another 4, and I get 64. So I had 1, 2, 3 4s. So x is really equal to 3. 4 to the power of 3 is 64. Or it would be like this, right? Log 4 of 64 is equal to 3. Okay? Now it's much easier to think about them in their exponential forms until you know the properties. Okay? And we're doing this because I want you to get a little bit more comfortable with logs before we start to graph them, before we do the properties. Okay? Now the second one, log 5 of 0.2, thinking about it as a 0.2 is not very helpful. Let's bring this to log 5 of 1/5. And now I'm starting to see, this base number kind of match up with that 5, and that could be kind of helpful. I'm going to set this equal to x. I'm going to think about it in terms of its exponential function. 5 to the power of x is equal to 1/5. Okay? Now, this is, interesting, right? Because we think 1, 2, 3, 4, 5. We're thinking 5 times 5 is 25. 5 times 5 times 125. And we have a fraction. So that needs to trigger your negative exponent here. okay? Because the negative exponent is going to bring that number to the denominator. And when I think about this really makes sense that x is equal to -1, because if I put a -1 there, it goes to the bottom as a positive, okay? All right, let me give you guys two to do, all right? I know it's kind of early in this, all right, but I want you to convert these. I want you to just do both of them now. Convert these to their exponential form and try to solve them, all right? They're a little tricky, but try them before I do them, okay? And if you get stuck, that's all right. I'm going to go over it. So give it a try, and then I'll go over it. Okay, so hopefully you guys gave that a try, all right? You set this equal to x, right? And we're going to write this in terms as exponential form. So this would be, again, think of it this way, circle method. 1/5 to the power of x is equal to 125, okay? Now, if you think about 1/5, well, if I just take my base and start multiplying it a bunch of times, it's not really approaching the number I want, right? Because 1/5 multiplied out 3 times gives me 1 over 5 times 5 times is 125, okay? It's almost like I went the opposite way. And this, again, needs to trigger that negative exponent to you, okay? I need something negative to flip this. And I already know that it should be 3, because 3 5s gives me a 125, so it just needs to be a -3, okay? So that's what x would equal. Now this one on the right, log 36 of 6. This one's a little tricky to think about, okay? And I want you to start to see why we don't always look at it this way and why we're going to use those properties later, okay? And yeah, so let's look at this, right? Write this, set this equal to x. 36 to the power of x is equal to 6, okay? And you might be going, well, how, if I do 36 to the power 1, that's 36. 36 to the power 0, that's 1. How do I get to 6? And you have to remember that when you take anything to the power of a fraction, it's like taking the root of it, right? So if I take, 4 to the power of 1/2, that's the same thing as saying the square root of 4, back to our exponential properties from many moons ago, okay? Yeah, so this actually works for this one. If I take 36 to the power of 1/2, okay, well, that's the same thing as saying the square root of 36, and the square root of 36 is equal to 6, okay? So x is equal to 1/2. And you're going to need to be able to think of these as, to the power of fractions also, okay? All right. Now, let's segue here. Let's move into transforming a logarithmic function. So here we have our kind of standard form, all right? And if you're noticing, again, it is exactly like the other ones in the way that we transform them, which is why we teach you to transform functions. As you can see, when you learn one, it becomes very easy to know how to do the others. We have our stretch here again. We have our compression here again. And we have our reflection here. Okay? We have our base number, just like we did in the other one, all right? Because that was kind of new with exponential. We had to think about our base number also, right? And then we have our horizontal translations, and we have our vertical translations, okay? Now, because we have this addition of the base number, when we think of our parent function, we really have to go an extra mile here. And we can talk about that again, actually, right? You need to first, when you think of these parent functions, take your log b of x, okay, as your parent function. So let's write that. That's not the best handwriting. Log b of x, okay? And then apply your a, and then apply your h and k, just like we did with exponential, okay? Okay, so let's try graphing our own, right? So let's extract our parent function. Whoa. Okay. Let's extract our parent function, log 3 of x, all right? So let's write that down here. Parent function is log 3 of x, okay? And, okay, let's extract our parent function. We have our parent function log 3 of x. When you try to think about how do you graph log 3 of x, it's all of a sudden very confusing, right? Like, what on earth gives us this, right? So let's convert this to the exponential form just like we did with evaluating. Let's plot that. And then because log is its inverse, we can flip all those points, okay? So in the inverse, log 3 of x, we flip the inputs and outputs. So they look like this, right? As the inverse. And if I rewrite this in exponential form, I get 3 to the power of y is equal to x. But if you remember, because we flipped the, if you think back to finding the inverse of a linear function, you had to flip the points. This is really 3 to the power of x is equal to y for the exponential form. It's still this for the log, but because these are inverses, I have to flip those x and y's when I go between them, okay? So let's use this. 3 to the power of x is equal to y. And let's graph it like we would have in the previous lesson, okay? Let's make a t-chart like this, okay? And I know I used 5 points. I'm going to use just 3 here, -1, 0, and 1, just because we have a lot more to do. And if I think -1 plugged in, that's 3 to the power of -1, which is equal to 1/3, right? 3 to the power of 0 is 1, 3 to the power of 1 is 3. So these are my points, right? Well, for the inverse, let's jump back over here to the left. Log 3 of x is equal to y, right? I need to flip those points, okay? Now I know I'm writing this as x and y, and I'm writing this as x and y, okay? But we do just flip them again, all right? So this goes -1, 0, and 1, because the x's are now the y for the inverse. And then the other one goes 1/3, 1, and 3, okay? So these make it over to the log's x's, okay? Now this explanation I've given you here does not feel like my best. So let's kind of recap this for a second here, okay? The first thing I did was I extracted log 3 of x so I can have my parent function here, okay? Thinking about things in terms of logs is very complicated, so I converted it to exponential form, okay? But when we go between, these forms, and evaluating, we don't really care about flipping the variables. But when we think about them as functions with outputs, we care. So I flipped them again so I can think about my exponential form as, x being my exponent and y being my output. Okay? I use this exponential form to find my parent points, right? Using -1, 0, and 1. Plugged those in, and I got out my y. Okay? Then, because these are inverses, okay, I can just flip their points, right? So I flipped them. I brought my x's here to the y, and I brought my y's here to my x's. So now I actually have my parent points. Is that a lot of work to get your parent points? Yeah, it is, okay? So let's plot those first, all right? So I got -1/3, which, it's like barely right here, right? Just +1/3, sorry. It's barely right there, and then -1. So that's that point, okay? I have 1, 0, and I have 3, 1, okay? Now, just for an example's sake, okay, I'm going to plot the exponential ones, right, which was -1, 1/3, okay, 0, 1, and 1/3. And look at this, right? You can see clearly that they're inverses, right? They're just flipped, okay? And if you remember, exponential functions went like this, right? And we never cross 0 here. Don't cross it. So it's the same thing here. This is going to go like this, and it's now just not going to cross the y. Your exponential function didn't cross the x, so your logarithmic doesn't cross the y, okay? All right, let's get rid of some of that, and let's keep graphing our function here. In fact, let me put that vertical asymptote in so we can see it, okay? Now we can go back and times these by our a value. So I have 1 times 2, 0 times 2, right? And then I have -1 times 2, okay? Which are all our y values. So I get 2, I get 0, and I get -2, okay? So let's put these in red. I have 2, This one didn't change. And then I have negative, let's see, 1/3, 2, right there. Okay? So you can see that it went from this to just being more out. Okay? That's your stretch. Okay. Now all we have to do is apply our horizontal translation and our vertical translation. And it's still the opposite. This is -1. So that means we're going right 1, and then we're going up 4. So I'll do that in green from the red point. So right 1, 1, 2, and then up 4, yeah. So 1. Let me do that in my pointer so you guys can see. So right 1, that's not my pointer. Right 1, up 4. So I'm going to be here, okay? Let's do that actually in purple. And then right 1, up 4. Right 1, up 4. Now because I went right 1, my vertical asymptote shifts right 1, right there. And now I can plot this. Okay, it's never crossing here, it's just getting closer and closer, and then it's going to go out to the right. Okay, so that was a lot of work. Definitely a lot of work there. It was the first time through explaining it. I really am trying to hit logs hard, but I think it'll get clearer as we go through. Okay, so we have another problem here. It's a we do. I know this one looks a little bit different, so I'm gonna kind of start this one off for you guys, and then you can, finish this one. Okay, but I want you to notice something here. There's no number here. All right. When you see a log with no number, that means it's log base 10, okay? This is called the common logarithm, all right? And I'm going to talk a little bit about that at the end too, but when you see no log number, it's the common logarithm, it's base 10, okay? So if I want to rewrite this, it would look like this, okay? Now let's leave it rewritten like that. Let's focus on grabbing our parent function here. Okay, and I think, well, I'll go a little bit further with you guys, okay? We want to convert this to exponential form so we can grab those points and then just flip them, okay? So we have log of 10 of n, so log 10 of n, all right? And we could just set it equal to an arbitrary variable. We could just set it equal, you could really think of it as g of n, okay? But then thinking it as 10 to the power of g of n is kind of weird, right? So we can just call it y, all right? We go to exponential form, so this is 10 to the power of y is equal to n, but really it's 10 to the power of n is equal to y. Now, if using different variables is super annoying to you, then hey, x, y, okay? Whatever you're comfortable with, all right? Now, we're gonna get our parent points here, so let's go n, comma, y. We use -1, 0, and 1. And if you think about it, 10 to the power of -1 is just 110. 10 to the power of 0 is 1. 10 to the power of 1 is 10. Now I do it the other way, okay, which here is still n and y, but they're technically flipped. I put -1, 0, 1 on the y's now, and then 1/10, 1, and 10 on the left now, okay? All right. So that's a lot of stuff there, right? And yeah, let's graph this. Okay, I think you guys can carry it from here. So why don't you guys pause it? So pause it and give this a try. See if you can finish this. Okay, so we're gonna have to go and graph our base value here, right? These points right there, and we have 1/10, which is just barely out there, and -1, so we'll just call it right there, okay? We have 1, 0, and then we have 10, see, all the way over here, and 1, very quick right there, okay? So this is moving pretty fast, right? Now, we need to apply our a value, which we see here is a negative, okay? So it's a -1, we can think of it as. So we can go to all these values and times it by -1. Now here, we have 1, 0, and 1. Okay, so 1 times a -1 is just -1, 0 times a -1 is just 0, and then 1 times -1 is, -1 times -1 is +1. So all these flip. So this goes up here, this stays the same, and then this one goes down. All right, so our logarithm now is the opposite, okay? Now the last thing is we have a horizontal translation of +2, which really means we're going to the left 2. So in green, we're going to take all the red ones and go to left 2. So that's here, and that is here, okay? That also means that my vertical asymptote shifted to the left also. And when I go to graph this, it'll be like that, okay? So again, a negative a value reflects your graph over that x-axis, okay? All right, we got one more, and then I got some math talks. It's shaping up to be a long video, and I'm sorry about that, all right? Okay, so we got one for you guys to do. We got 2 log of 1/2 h minus 4 on the outside there, okay? So why don't you guys pause this, give it a try, and then we'll go over it, okay? Okay, so hopefully you gave this a try, all right? If you got confused, that's all right. We have this as our base here, okay? So we have log of 1/2, and I'm just going to use x because I think it's more comfortable to use, is equal to y. I convert this to exponential form, which means I have 1/2. Now it's looking kind of weird, right? To the power of y is equal to x. Because this is our inverse, we really need to think of this as 1/2 x is equal to y, okay? I make a t-chart, x and y, and I use my apparent points of -1, 0, and 1. Now when I plug in -1 into x, that's 1/2 to the power of -1. Well, that really just flips it, right, to equal 2. Now if you're confused by that, remember, you apply that -1 to the top and bottom, that becomes 1 to the power of -1, 2 to the power of -1, which just flips it to 2 over 1, or just 2, okay? Now anything to the power of 0 is 1, and then again, 1/2 to the power of 1 would just be 1/2, okay? Now I need to do the inverse of that, okay? So I have again x and y. My y is now -1, 0, and 1. I'm flipping these, right? And then I have 2, 1, and 1/2. So now all I need to do is go and graph those points, okay? Let me actually just go back here real quick. Yeah, I did that right. Okay. All right. Now, we got 2, -1. So that's 2, -1 here. We have 1, 0. That's here. And then we have 1/2, 1. Okay? So it's shaping up to look a little bit different here when we have that half, okay, as our base value. All right? If we were to have if we think about this, if this was a 2, okay, down here, and I plug that in, I would get 1/4. If I had a -2, I'd plug that in and I get a 4. Sorry, I'm trying to do more points so we can get a better picture of what this looks like. Okay, so 4, -2 is here, and 2, 1/4, 2 is here. So you can kind of see that it's still bridging here, and then it's going off that way. Okay, so it's looking kind of interesting, right? All right, you have to apply your a value, which is the multiplying all these by 2. I'm only going to focus on my base points again. So I have 1 times 2, 0 times 2, -1 times 2. I get 2, 0, and -2. Okay, so let's put that in green. So 2, 0, and -2. So we can see it just stretched. And then I have a -4 on the outside, so I'm going to bring all these down 4 spaces, all the green ones. So that's here, here, and here. Okay? Now my my vertical asymptote did not change places, so it's going to go like this. Okay? All right, that was a lot of work. This should probably be a long video, or maybe I've just done a lot of retakes tonight. Oops. Okay? Okay, so we're going to skip the Desmos exploration. I normally like really doing these, but I think it's a really long video, and if you guys want to see it, we can start class off with this, okay? And if you want to see that, leave that in the feedback, okay? Now, couple little math talk here, all right? For starters, you heard me refer to the common logarithm, okay? And that's, we see base 10 so often that we just going to call it that as common. And so instead of writing 10 all the time, we're just going to leave it as log of x, okay? When you see no base, that really means it's a common logarithm. It's base 10, okay? Now, I told you guys, mathematicians, we're lazy. If we see something that's super common, why write it all the time when we can just go, hey, you know what? When we leave it out, it's really there, okay? Now, the other one that you haven't seen in this lesson, but you're going to start to see soon, is called the natural logarithm, okay? Now, the natural logarithm has a lot to do with a special number called e, which is Euler's number, which we're going to talk about this in 7.4, okay? Now, Euler's number is a very, very special number for exponentials, and instead of writing this out, we just are going to go ln of x. So when you see ln of x, it really means that the base is e, okay? Which we will get to this in future lessons, okay? If you did any research, I wanted you to know what these were, okay? Now let's talk about why are you learning about logs, okay? There's obviously the very quick answer of, well, it's the inverse of exponentials, right? And so here you can see we have an exponential, and that's actually 2 to the power of x. And so then this is the inverse of that one, okay, of that exponential. So if we were solving equations and it had exponentials in it and I have to solve for x, you're going to need logarithms, okay? So that's kind of the first answer of why you need logs, is to solve exponential equations, okay? But that answer is really just saying you need this math to do more math, right? Let's think about searching and sorting data, okay? When you come up with a sort, like sequential sort, binary sort, BOGO sort, don't use that one, right? They follow a function pattern for time complexity, okay? So let's say I created a sort and it followed an exponential pattern, all right? And if this is the amount of numbers being sorted, so like let's say I had 1, 10, 12, 3, 2, and just on and on and on and on, right? Each number, that would be the number sorted, and I'm trying to sort these from lowest to highest, okay? So numbers being sorted, and then time to sort in seconds, okay? If I want to here with an exponential sort, already at 2 to 4, look at my huge jump in time. And then if I go from 4 numbers that I want to sort to 6 numbers, it's already off the Richter scale. This is going to take forever to sort. If you think about companies like Facebook, Google, imagine how much data they have to sort and filter through. An exponential sort is not going to work. If you think about a linear sort, right, every single time you add more data, you get an exact increase in the time that it's going to take. So 10 numbers takes 10 seconds, right? 20 numbers takes 20 seconds. You might think that's okay, but if you have to sort a billion numbers, a billion seconds is too long, okay? This is where logs become so absolutely important, is if we can create a sort or even searches that follow the logarithmic pattern, then look what happens when I double data down the line, okay? So here when I go from 2 to 4, I'm at about, 1 second to 2 seconds? So I doubled my data and I doubled my time early on. But when I go from 10 to 20, right, look at the small increase there, right? And then I go from 20 to maybe 40 to 80. It's just barely going up. So I can add a tremendous amount more data. And yes, I'm still adding time to search it or sort it, but it's far less time, okay? In computer science, logarithmic is everything, okay? So I hope you guys enjoyed this lesson. I hope it's not too long, and I hope you see those 2 reasons on why you're learning this, okay? 1, to solve exponential equations by using the inverse logarithm, right? And then 2, the applications in the real world are super, super important, all right? So everyone, I hope you guys have a great time, and I'll see you guys next time.